Okay, so the idea today is to review some basic concepts about thermodynamics. Thermodynamics is a core discipline, it's a core science for all of chemistry and biochemistry. And we are going to use it in a very substantial way during this course. So the first basic concept about thermodynamics, although historically that's not the way it was introduced, let's try to think for a moment of a container with a large number of molecules. It's interesting to know that many of the things we can say about thermodynamics do not require, not even the concept of molecules. We can write equations in thermodynamics thinking of them as empirical equations and without resorting to any molecular model. And this is exactly how it was developed historically. It was developed by engineers trying to solve the problem of efficiency of heat engines and steam locomotives. But let's think for a moment about this. Let's say that we have a container, and this container has a certain volume, and we have a certain number of particles. Now, in general, for a thermodynamic system, the number of particles is going to be of the order of Avogadro's number. So, of the order of 10 to the 23 particles. And this is the case for a macroscopic system. Of course, for a microscopic system, then the number of particles is going to be, it could be very small. It could be even one particle. So we have this difference, this important difference. And in many cases, we are going to talk about the thermodynamic limit. The thermodynamic limit, it's very large number of particles and a volume, a macroscopic volume, in such a way that the density, that is the number of particles over the volume, has a well-defined value. But we talk about that later. At this point, what I want to stress is this. If we want to specify what is called the state of the system, the state of the system, so there are at least two ways to do this, and it's interesting to look at the difference. If we want to specify the macroscopic state, then for each particle we need, let's say in classical mechanics, we need to specify position. So we do the position vector, 3 coordinates, x, y, and z, let's say in Cartesian coordinates. And then we need to specify the momentum for each particle as a function of time. This is time. So then you see that if you want to specify the state of the system doing this, you need 3n plus 3n numbers. You need 6n numbers. Now you realize that if the number of particles is Avogadro's number, this is of the order of 10 to the 23 data points. So this is way more than any computer system can handle. So what we learn from here is that if we are looking at the simple system with an Avogadro with a mole of particles, then if we wanted to specify the macroscopic state of this system, we will need a huge number, 10 to the 23, to specify the state of the system. As it turns out, in thermodynamics, so now we go to the thermodynamics. It turns out that we can specify the state of the same system given a very small number of variables. And that is, you will have to specify the number of particles, the volume, and a quantity here that is going to be what is called the internal energy. So we use the letter U or E to refer to the energy and the internal energy. Now, in thermodynamics, we are concerned, at least in equilibrium thermodynamics, we are concerned about a very particular set of states which are called equilibrium states. And equilibrium states, you see, time does not enter here. Equilibrium states are independent of time. This is the state a certain system reaches when all fast processes have already happened. So the equilibrium state depends on number of particles, the volume, and the internal energy. So you see the huge simplification. If we are thinking of a box or a container with a mole of gas molecules, we don't need the information about what the individual molecules are doing. We only need the information about the number of particles, the volume, and the internal energy. And this is enough to specify the equilibrium system. So the first statement, we might call it a postulate about thermodynamics, is that there exist equilibrium states in thermodynamics which are specified by the number of particles, the volume, and the internal energy. And if we have, in this particular case, it's only one component. If we had two or more components, then we will need the energy, the volume, and the individual number of particles for each component from 1 to R. So this is kind of the first introduction to this fundamental idea. The second important point, you might call it second postulate, is the concept of a constraint. So imagine that you have a container, we have particles on the left side, molecules, and then the right side is empty. So there's a vacuum here. So now this wall here that divides this part of the system from that part of the system, this is called a constraint. In this particular case, it's a wall. So now we have system, let's say S, system, let's say S prime, and this constraint prevents these molecules or the gas from going from the left part of the container to the right part of the container. So now it comes what is called the central problem of thermodynamics. Imagine that initially this system is at equilibrium. So it will be characterized, as we said before, by the energy, the volume, and the number of particles. Now imagine that we remove the constraint and we allow the gas to expand and occupy the empty part of the container. The central problem of thermodynamics is what is the new equilibrium state once the constraint has been removed. This is the central problem of thermodynamics. This simple statement, what is the new equilibrium state once the constraint has been removed, or the constraints have been removed if there is more than one constraint. And there are many examples of this. So, for instance, the constraint could be that you have a part of the system at a certain temperature, TA, and another part of the system at a different temperature, TB, and there is a wall here that prevents no heat flow. So if this is the constraint, this is an insulating wall, and initially you will have equilibrium. So this system will be at equilibrium, this system will be at equilibrium separately, and no interaction. If you remove the constraint and allow heat to be exchanged between these two, what is the new equilibrium state? It turns out that the new equilibrium state is going to be TA equal to TB. And again, in this process, removing the constraint and finding the new equilibrium state, time is not involved. So this process of equilibration might take 1 second, 1,000,000 years, time is not involved. In the description of thermodynamic processes, The only thing we are interested is once the system, the overall system, reaches equilibrium, what is the new equilibrium state? And this is a very important distinction between a dynamical description of systems that involve time and a thermodynamic description that does not involve time. So this is the end of this first lecture.